now that we have our full solution, we can focus on the exterior of the body, which is given by this expression. Okay, remember that's the region B, which represents the exterior of the body, which is relevant because if we are constraining measuring local constraint of our gravity, we can take, for example, the Earth, and we are studying, for example, the orbit of the Moon with extremely high accuracy, and the Moon is outside the Earth. Therefore, we need to look for the region B, which is given by this expression. But what do we notice? We have the solution, everything is done. Not quite, because if you look at these two terms, they are not quite explicit. Therefore, we want to make these two terms explicit and possibly have them as a function of the coupling Q. Let's see. Let's do that. So, as I said, we focus on region B, which means we are going to consider this equation, and to have it in an explicit form, we need to derive this difference. This can be easily found because we can look at the value of the derivative of the potential between the region A and the region C when they touch each other. Remember, this is region A, region C, and here they must be equivalent, right? Therefore, the derivative of the effective potential here coming from this side or coming from this side or coming from this side must be the same. Nice. Therefore, let's do that. So this is the expression for the derivative with respect to phi of the effective potential for region A and region B, as we derived them earlier, and the two must be equal one with respect to each other. Therefore, this is region A, this is region B, and we set equality. Then what we have, an expression of phi that we are going to be the one at RA, but this must come from equation A. Remember that this is from region A. So here we have to plug this expression. Okay? This expression where here, and here we have RA, because we are looking for the touching point between the two regions. Okay? So we get this expression and we plug it into here. Okay? Nice. If you do that, you get this lengthy expression. You can work it out a little bit. For example, this guy and this guy cancel out. Then you have m1, m to the power of 2, and they cancel out. And you obtain, after isolating this term, you see I'm just isolating this term, you get this simpler expression, out of which you can easily read the difference between phi b and phi a. Phi b and phi a that we can now plug here and here. Okay? So you see? Now we have an explicit expression. I spare you the super mega boring details, but in the end, you see this is a constant that can be rewritten in this term. So you see, this constant is that, where we identify this Q effective with this expression. That's the guy which is going to define the equation of motion of massive object. Okay? Look what we have. We have Q, which is the bare coupling, minus all of this guy. Okay? Good. How can we then get this screening? As I said, we must have Q effective such that the behavior of body in the vicinity of overdense regions is unaffected. Okay? Q might be large, but this guy could be small. Okay? Or could be such that the equation of motion of body is not affected. Meaning, our theory, even if it has a strong intrinsic bare coupling, it's basically giving predictions which are very, very close to general relativity. Let's study then the motion of bodies within this theory. And therefore, let's look at the fifth force. Remember, in previous lecture, in previous video, I showed you how to derive the fifth force, which is just given by the gradient of the potential where the Q factor, the coupling, is coming in place. Okay? In this case, the field phi is given by our expression that we derived, the expression which is valid outside the body. Therefore, we just plug our expression for the field phi here. And that's what we get. Okay, so we have the first term, gradient of phi, which is going times q, which is going to give us that. Phi b is a constant, remember that is flat outside our body, and therefore this is equal to 0. Pop, it goes away completely. Then what we have? We have this guy. So we have the derivative, so that's in radial, so the gradient in radial coordinate becomes just the derivative with respect to r. So we have q, which goes here, the 2, which is this one, q effective, which is this one, and then we have the derivative with respect to r of our potential phi, which is what is left. So gm over r squared. And look, there is a plus which is popping up here. Okay, that's because there is the r to the power of minus 1. That's our force. Okay, so you see there is a proportionality that enters here. So the force is not given only by Q, but is given by Q times Q effective. And therefore, if Q effective is small, this contribution could be very, very small and within the error bars of the measurements of the local gravity constraints. Okay? That's the trick. Therefore, you understand that in general we do not have the screening mechanism, we have only if this guy is very small. Therefore, let's give a look for the condition of having the screening mechanism. And again, as I said, that's the guy, and this happens when this is small. When RB minus RA is much smaller than RB, meaning this is negligible, and RA over NA RB much larger than 1, meaning this one is negligible. Okay, such that this one is much smaller than 0 because of that, and this one is much smaller than 0 because of that, such that all of this is very small. Okay, such that the fifth force is very small, is within the error bars of our local measurements. That's the trick. Last little bit of information that I'm going to give you is the thin shell parameter. Okay, you understood already everything, how the screening works, how it's come about, how we can have it on place, what are the constraints to our theory such that we have a screening in place, but I would like to mention this parameter because it's likely that you find it in the literature. Okay, so how does it work? So first of all, if we have a screening in place, that's the case whenever these two conditions are fulfilled. Therefore, what we can do is to set equation 1, which is this this expression here. Okay, we just set it to be. So we just expand it using these limits. Okay, if we do so, this equation becomes that. Okay, so this equation, you see, we just use this guy, it becomes just that. Okay, that's what we did. In this step, I just did an initial, writing the things in a nicer way. I related rho a to rb to the power of 2, which is popping up here and here, to the potential, to the gravitational potential at the surface of the body. Such that I can have it here instead of this, if you want, more obscure rho a to rb. Okay. Then what we do is we divide this expression with 6q phi b. You see, we have phi b, now we divide by sqp, we obtain that. This guy goes away, we bring it on the other side, and we have this expression and this expression. This expression is this one. Remember that also this side has to be divided by 6q phi b. So this expression is just this equation with the approximations that I mentioned, nothing more than that. And this is a definition. We call this ratio thin shell parameter. It's called thin shell parameter because if this one is dominant with respect to that, it is just expressing how thick is this region. Okay, you see this is just the difference between these two. This is just to give it the name. Okay, good. With this expression, you see we have our phi A, phi B, and phi A. We can plug it in our expression here with the approximation, using the approximation that we mentioned, and we obtain this effective coupling term, Q effective, which is proportional to the thinness, to the thin shell parameter. Therefore, equivalently, you can say we have a screening mechanism when these two conditions are met, or we have a screening mechanism whenever the thin shell parameter is much smaller than 1. Okay? So the thin length, the thin shell parameter is a way of swallowing in one parameter these two conditions. When this is fulfilled, then we have Q effective, which is much more than Q, and we got the screen that we were looking for.